Let's do another example. Here we need to find the power series representation of this term. So remember, this is our basic equation. And for this given particular function, there's a very easy method. It's like you can write down this function as x cubed multiplied by 1 over x plus 2. And we have already found the power series representation of 1 over x plus 2, which is this one. Now this results you don't have to remember, like you don't have to memorize, okay? This is the only equation you have to memorize, right? So through this one we already obtained this result, right? So if they have given this as a question, this as an original question in the exams and or in homeworks, you will have to derive the power series representation of this term separately, okay? But as we have already computed it in the previous video, now we can directly use it here. Okay, so anyway, now we have the power series representation of this term. So it's just a matter of multiplying the power series representation of this one with x to the power 3. So then these constant terms will stay the same and you will get x to the power n plus 3, because x to the power n times x to the power 3 will be equal to x to the power n plus 3. Okay, so this is the power series representation of x cubed over x plus 2. And now remember, this representation was valid for the x within this region, for the modulus of x less than 2. That means this equation is true for this interval, and that means this equation is true for this interval. That means the power series representation for the new function will also be true within the interval of the previous series. That is only because you are using the same power series for this one, and that power series is only valid within this region, right? Okay, and I need to teach you one more thing related with this series representations, right? That is called shifting of the index, right? That's a very small thing, right? But now it's like this. Now when you expand this series, you will get terms like this, okay? But now you can see that within the series representation you have a x to the power n plus 3 term, right? But if you feel more comfortable with, now the original power series representation was something like this, okay? You don't have any plus terms in here. So if you are more comfortable with writing it as a power nth term, we can still do it. We can do some index shifting and rewrite it as n to the x to the power n without this 3. But you should do it very carefully, right? Now since this is the expansion of the series notation, we can see that if we write a series representation and if we have x to the power n, right? And in order to get this, in order to get these terms as the result of the expansion of this series, we will have to start the indexing at 3, because then only you will get this one as the first term, right? Now see, here we have written x to the power n. But the thing is, now if you just write down this term in front of this x to the power n, then the things will go bad, right? So if you just write down this term, then see what will happen. when you try to expand now for n equals 3, you will of course get x to the power 3, which is this term, and now that is correct. But how about the other terms? X negative 1 to the power 3, that is negative, and here you will get 2 to the power 3 plus 1, and that is 4, and that is equal to 16. So the coefficients does not match if we just write down the coefficient of the previous series. So we have to do some changes for that as well. So here it's like we reduced 3 from this one, right? So we have reduced 3 from the from the power of x, right? So we have to do the same thing for all these n terms as well. So if we reduce 3, and if you just write n minus 3 here, and here also you have the 2n plus 1, and if we minus 3, if you reduce 3, you will get n minus 2, right? So if you write n minus 2, then you can see that by expanding this series as well as this series, you will get the same set of terms, right? So this is called shifting of the index. See, here we have reduced 3 units from the index of this general term, but to counterbalance it, the starting index was increased by 3, right? So if we are increasing this one by 3, we will have to reduce all the representations of n terms by the same quantity. So the best way to figure it out is to write down a couple of terms from the original series representation, and then write down the new series obtained by shifting the index, and just expand this one and see whether you get the original terms, right? So it's better if you are familiar with these index shiftings, because it will be useful sometimes, right? Okay, so as a result, we can even write down the power series representation of this function like this as well, right? See, here we start at 3 and we have x to the power n, but still you will have the same domain for this equation.